recording. Okay. As I said, you're talking about the parity method, how to generate residuals for a given system. And the system is in time domain. And we said that we need to differentiate input and output q times and put them in a vector in the rows and of a vector. And we ended up having this equation. And I said that because in the residual, we shouldn't have x and d. Somehow we need to actually get rid of this term. How to do that? Because you have a matrix here. It's O and T is a matrix. Each one of them is a matrix. They have also augmented together, but still it's a matrix. So we need actually to find the left null space of this matrix. And then when you find the null space, then we select W in that null space, because as I showed you, null space doesn't have only one element, but each one of the elements of the null space, or each one of the members of the null space you select, when you multiply W by this matrix, it would be 0. Okay, so you select W from the null space and left null space, then you know that if you multiply W by this matrix, it would be 0. Therefore, what you end up with is W. Okay, we have multiplied W from the left, both sides of the equation. So in the left, we have W multiplied Y, Q. And in the right, we have W multiplied this term, but because it is 0, I have ignored that. I've not written that here. Then we have W multiply TU multiply U, and W multiply TF multiply F. So this is actually what we have. So again, this is I have repeated that. So now we have this equation: W multiply Y is W multiply T multiply U plus W multiply T multiply F. If F is 0, then we have W multiply Y is equal to W multiply T multiply U. So if I move this W multiply T multiply U to the other side of the equation, so and I name it, or I define it as R. So let's see what we have. W multiply Y minus W multiply T multiply U. If it is R, you know that if there is no fault, so if fault is 0, then R is 0. If fault is not 0, then R is also not 0. Okay, so comparing to what I said at the beginning, I said we need to multiply Y by a WY. So WY would be W, but WX would be minus WTU. Okay, so basically we needed to find a matrix to multiply by the vector of Y and its derivative, and then add it by a matrix multiplied by U and its derivative. Now we have calculated these two matrices that we were looking for. One is W, the other one is minus W multiplied T. And we believe that actually this R we have generated here, this residual we have generated here, is having the properties that we have, because you can clearly see that when fault is 0, then R is 0 as well. And when fault is not 0, then you will get R equal non-zero, because the left side minus this one is 0 only if F is equal 0. If F is not 0, then R would be equal to W multiplied TF plus F. Is there any question? Is there any part that I need to elaborate more? If you got the concept, of course the details, there are a lot of equations. It's not easy actually to follow the details, but through an example, I believe it would actually get more clear. But the concept should be actually clear now. That the main trick we used, we wrote this matrix, and then we found W in the left null space of that matrix such that we can actually ignore that term. Not ignore, we can actually remove that term or eliminate that term.
I have a question.
Okay.
Why do we need the residual to include the W y bar term? Why can we just not have the residual be the WT times default? Because that's the only term that matters, right? I mean,
residual can include y and u. We don't have to have y and u in the residual, but if you think about that intuitively, you have a system and you want to know if a fault has happened to the system, and the only way we can do that is to look at what input has been and what output we have got, and somehow by actually investigating the input and output of the system, we can realize whether or not a fault has happened. So to use u and y is quite intuitive. But if the question is why we need to have the derivative of y,
and that I understand. I don't understand because, as you said, if the fault is going to be 0, the two parts are going to cancel out, and the residual is going to be 0. But the parts are going to cancel out no matter what, right? Like whether the fault is non-zero, the other two parts are going to cancel out either way, right?
Okay. What is W minus W? What is WY minus WTU? What is R? If you move this term to the other side of the equation, then this term is still left in the right. So R is equal to this one, which is equal to WTF. Am I right? Can I annotate here?
I think I get what you mean. I think I misunderstood the thing. I think I get now.
Yeah. Okay. Let me switch the. See if camera is open. Yeah. Okay. What we have is we have basically W. And by the way, because I'm using the slides of one of my colleagues that is also teaching the same course in Aalborg University. So most of the slides is actually from him. I have added some small details to that. So the notation that he has is for a vector, he has a line on top of the variable. So I prefer actually to have this underline, but because it was in the slides, I didn't change that. So this y bar is actually a vector. This bar shows that we have a vector, by the way. Okay, so this is what we have. W multiplied y is equal to W tu u bar plus WTF f bar. I will drop the arguments just because I just want to get the we need just to get the idea. So this is what we have. So we define R, the residual, to be WY minus WT U bar. This is how we define the R. But if you look at here, if you move this one to the left, actually R is equal to WTF, which means that R is equal to WTF.
Yeah, that's exactly what I meant. That's
yeah. This is missing actually in the slide. I agree with you.
Okay, good.
So No, it means that if f is 0, r is 0. If you have f, r is non-zero. Back to the slide. Okay. So it seems that actually we found what we wanted. And as I said, the key point was the knowledge space of this matrix. Now, maybe I can do that through the example, but briefly I can mention that why we needed to differentiate, because when we differentiate, we are actually adding more rows to this matrix. So if the matrix itself was invertible or was full rank, that we didn't have any knowledge space, by adding the terms to that, actually we are increasing the chance of making that not full rank, therefore it has a knowledge space. So we continue such that we get to the point that this matrix is having a knowledge space. So, okay. So because of that, at the beginning, we don't know how many times we need to differentiate. We actually need to differentiate, form this matrix. If it is enough, we don't need to continue. If not, we differentiate one more time. Okay, I have the algorithm here. That actually algorithm wise it says what the steps are. So basically for a system that is given and the matrices are known, these matrices are known, we know A, B, C, D, E, F, and we need actually to calculate the matrix W, and W, as I said, in the knowledge space of this matrix. So the first step is actually to form O, T, TD, and TU. How to form that? As I mentioned, we have these equations to form the matrix. So this is O, TU, TD, and TF as well. But uh, because at the beginning we don't know how many times we need to continue, as I said, you differentiate once. Basically, you don't differentiate. You just put in the vector here. You just put okay. You have C, and then you add CA. Just form that matrix. If it is full rank, you continue. So you add one row to this. Yeah, you need to form the matrix O, T, and T, TD, and TU. And later you need to form this matrix. Make sure if it is not full rank, it has a knowledge space, a left knowledge space. Then try to find a member of knowledge space. And basically, the member of knowledge space is the matrix W. Okay. Do you see, before I continue, do you see any drawback for this method?
Maybe it's somewhat sensitive to noise or sensitive to
Yeah, why?
high frequency because of the derivation.
Exactly. It is actually a big problem. Differentiating these signals because okay, differentiating U is not a problem because U is something that controls the sending. It doesn't have any noise attached to that. But differentiating the output, because output is always added with noise. So what we get from sensor is noisy. And when we differentiate, basically we amplify the noise because differentiation means the variation of the signal. And when you differentiate, I don't know if you was it in your class that I the other class, I mean SSP, that I showed you when a signal is added to the noise, and then when you differentiate, what happens? Was it?
Yeah, you showed it.
Yeah. Okay. So good. Uh, so that's actually the case. And if we need to continue and differentiate more, it would be even more problem because second derivative, yeah, it's hard to do that. So what we need to do, we need actually to design a filter, especially for Y. As I said, U is not problematic because it is not noisy, but for Y, we need to filter the signal and then derivative and then differentiate. So this filter also affects the residual. But anyway, it usually a first order filter works, and usually in many cases only we need to differentiate only once. I will show you in the example that only once, one time differentiating would be enough in some cases. And if it is the case, just a first order filter could be enough. I mean, it works okay. Just a simple filter and then differentiating and then forming the matrices. When we do this algorithm and then we simulate, or let's say we have an example and then we apply this, we need also to make sure or to check whether or not detectability of fault is weak or strong. How to do that? You just need to apply a fault, and a fault could be an abrupt fault, which means that a fault stays in the system, and then you plot the residual and see if the residual will stay in the system or it will damp after a while. Okay, that's the algorithm, and now I have an example. Maybe next session we can also simulate this, but I have it and also have the results. But if you like, we can simulate it in the next when the lecture is finished. Still, I have plenty of slides. Okay, we have a system, two state variables. A is 2 by 2, of course, and then we have B, C. D is 0. I mean, in reality, most of the real systems, they don't have UD. So also I have assumed that there is no fault applied to this equation, to the second equation. So EY and also FY are 0, but we have a disturbance and we do have a fault applied to the first equation, to the state equation. So the EX, the coefficient of disturbance is 0.11, and Fx, the coefficient of fault is 0.1. And if you look at these two, if they are exactly the same, then I talked about that the fault definitely is not detectable, because fault and disturbance, they are affecting the same way. Now, because they are affecting differently, so we can actually make it sensitive with respect to fault and ignore the disturbance. One more time, when you have a system, you don't have the disturbance, but you know how disturbance is affecting the system. So basically, you have this coefficient, but you don't know the disturbance. And the nice thing is that you don't know disturbance, and it doesn't matter how disturbance is changing, still the algorithm works. Okay, if we follow the algorithm, we need to actually form these matrices. So I have actually formed this O matrix, C and CA, but imagine that I only consider C, okay? Imagine that I have only the first two rows, because the first two rows are C, and the third row and fourth row are CA. If we only have C, I want to show you why we have needed to actually differentiating, why just using Y hasn't worked. Okay, if we have only C here, and then this TU matrix is the coefficient of U, it would be D0, so it would be 0, 0, 0, 0. And this is actually the matrix we need to form and see if it has a null space, a left null space, okay? So if we look at that, when we have only two rows, so the two rows, if you notice here, the two rows, because you have identity matrix here, the rank, if you have a matrix 2 by 4, because if we don't differentiate, what we get here, it would be a matrix 2 by 4, the first two rows of this matrix. If you want to know what is the rank of a matrix 2 by 4, first of all, the rank is maximum 2 when you have 2 by 4 matrix. The rank would be maximum the lower dimension. If you have a matrix, for example, 5 by 10, the maximum rank is 5. Okay, it cannot be higher than 5, that's for sure. But the point here is that whether this rank is 2 or not. So how to check it? If you can find a matrix, because you have this 2 by 4, just notice the first two rows here. Let me switch to You have a 2 by 4 matrix, for example, 1, 3, 2, 5, 0, 2, 1, minus 1, something like that. It is a 2 by 4 matrix. As I said, the rank of this matrix, what does rank mean? It means how many independent rows we have. Okay, how many independent rows we have. So the rank is maximum 2. So the rank could be 1 or 2. But if you want to know whether or not rank is 1, just if you can find one 2 by 2 matrix, it doesn't matter where it is. It could be the first 2 columns, or it could be first column and third column, first or last, the 2 last, doesn't matter. If you can find just one 2 by 2 matrix, now I have found it here, such that this matrix is invertible, such that the determinant of the matrix is not 0. If it is the case, then the whole matrix is full rank. When we say full rank, it means that the rank is 2. But I can give you an example of 2 by 4 matrix such that the rank is not 2. So imagine that you have 1, 3, 2, 5. The first row is exactly like this. And I double the first row, I write it here. So this one. It is a 2 by 4 matrix, but the rank is 1. Because you don't have two independent rows, because the second row is exactly a function of first row. So it's the first row multiplied 2. And any 2 by 2 matrix you select, determinant would be 0. So if you calculate determinant, 6 minus 6 is 0. Okay. So that's actually the idea, that when you have 2 by 4 matrix, if the rank is 2, then you need to continue because it is full rank. Now I go back to the example. Notice here. So I said that if we don't differentiate and we just have the first 2 row, now the question is what the rank of this 2 by 4 matrix is. So if you notice, the first 2 by 2 matrix here is the identity matrix, and the identity matrix is of course full rank. The determinant is 1, it's not 0. Therefore, it is full rank. Okay, because of that, we needed actually to differentiate. So we differentiate once, and then we get CA here. So CA will add this matrix here, and also you need actually to calculate the other matrices. So all of them you need to differentiate one more time. Not one more time, once, because the first one wasn't differentiating, was not the derivative of y, but we differentiate once for all of them, for u, for fault, and also for y. So if we do all of them, and then when we get this matrix, now the question is, we have got a matrix 4 by 4. The question is if the rank is 4. If the rank is 4, you need to continue. If the rank is not 4, if, for example, is 3, then you don't need to continue. Can you say what the rank is? Okay, it's written 3, but is it okay? The rank is already the solution is given here, but any idea why the rank is 3? Okay, if I mean in MATLAB easily you can type rank. It's a function in MATLAB, rank, and then you can give a matrix, and then if we give it the rank, but when you have a column completely 0, when you have a column completely 0, it means that actually the determinant of this matrix is 0. And when the determinant of a 4 by 4 matrix is 0, it means that the rank is not 4. But it doesn't matter if you don't remember from mathematics why the rank is 3. So I'm telling that the rank is 3. And because the rank is 3, then we don't need to differentiate anymore. It is not full rank. And which means that actually we can find a left knowledge space for that. And one of the elements of that left knowledge space is this. And as I said, if you find one element in the knowledge space, if you multiply all terms of this vector, by any value, it is still in the knowledge space. So for example, minus 20, 100, or 104, minus 20 and 2, which is W multiplied 2, is also a solution. So it is not a unique solution you find. It's a knowledge space is having infinite elements. So you just select one element, and this W is the one. So if you multiply by that matrix, it would be 0. So why do I need to calculate W multiplied T? Because it is the coefficient of fault. It was here. So R is basically W multiplied T multiply F. So I have also calculated W multiplied T. Why do I need to calculate? Because if it is not 0, because we should make sure it is not 0. Because if the coefficient of fault is 0, then again it's useless. Because the residual should be a function of fault, and the transfer function from fault to residual shouldn't be 0, which here is not 0. And it is not only it's not 0, it's a constant value here, 1 and 0. It's not a function of time. In principle, in general, it could be a function of time, but here it's not a function of time, which means that if you have a fault, imagine that fault is 0.1, okay? Then residual would be this value multiplied fault, which means that residual will remain non-zero, which means that you have a strong detectability. I hope it makes sense. Because this value, this is the coefficient of fault. And then if you multiply by fault, you will get residual. So if fault is non-zero, and then you multiply this by fault, it is not a function of time. So there's no reason that actually this one disappears. So it will stay. It will stay, so the residual will stay non-zero if a fault happens. Because of that, in this example, you have strong detectability by designing a residual generator using parity method. I have also simulated that. In this simulation, actually, I have applied a fault at time t equal 10 seconds. And you see that you will see this deviation in the residual. So the residual has been 0. Now it is non-zero. But I also mentioned that at the beginning of the lecture. In this lecture, today's lecture, we don't consider noise. But remember that in reality, you don't get residual that clean. It's not clean like that. It is noisy. So even when it is 0, it's noisy, and also when changes the value is still noisy. But from the mean value, for example, we can check the mean value. We'll talk about that. How to make decision. We will talk about that. The focus of today's lecture is to generate residual, but to making decision on the residual, and then it would be actually the topic of next session. Any question? Parity method can be done in the. Okay, go on.
I have a question. Is it possible that we don't get to have a null space?
When you continue, you will.
I mean, if we continue, but you said that we can continue until the n-1 derivative, and I'm just asking if is it always possible?
If it is detectable, yes. If it is not detectable, no. But if it is detectable, yes. Also, because let me. I mean, the format of these matrices are such that actually you're increasing the chance to get that. So I wanted actually to see if I can show that here. For example, one of the reasons could be this D, as we saw. Usually in the real systems, we don't have D. So if we don't have D, and now we go to the example, you see here we don't have D. Also, we didn't have D in the first. I mean, if we didn't differentiate, it was 0. But having 0 only focus on the first 2 rows here. Having 0 doesn't actually change the rank because the matrix is full rank already. But if we continue, then having D equals 0, because D equals 0, you see D here? Having D is equal 0, actually, it is the reason that you, just by one time differentiation, you will get this not full rank. But you're increasing the chance, and as I said, if it is different, if it is detectable, you will get that one. Okay, I wanted to mention that the parity method can be done in the time domain and also in the frequency domain. In the time domain, the issue we have in the time domain is, of course, differentiation of the signals. But if you do it in the frequency domain, you will not need to differentiate the signal. Okay, so I'm going to continue the lecture, and this time the topic is parity method, but in frequency domain. Okay. Imagine we have the same system, the state equation and the output equation and the same matrices that we had. You know that you can actually, using superposition law, you can calculate the output in Laplace domain as a function of u, d, x0, and f. How to do that? You just need to take Laplace transform from the 2 equations you have. And if you take the Laplace from the left side, the Laplace of x dot is actually s multiply x of s minus x0, the initial value of x. And then if you take the Laplace from the right, then it's easily a multiply x. So in the left side, you have s multiply x, and in the right, you have a multiply x. And if you factor from x, you will get, and you bring everything to the left, you will get si minus a. I'm not writing that because I believe you have seen that. Anyway, if you do that and you use this superposition algorithm, you will actually see that y in Laplace domain can be written as this equation, and each one of these transfer functions are given here. So for example, HYU is the famous one that we have had in many courses. I mean, at least you should have seen that in COS. It's CSI minus A inverse B plus D. But also you can calculate for example, the transfer function from disturbance to output is this, and from fault to output is this, and you have all of them, okay? The idea is, again, to generate a signal, a residual signal that has the same properties we had. And the residual signal, as you can see here, to generate the residual signal, we can only use U and Y. So, because that's the only observations we have. So we use U and Y to generate residual signal, but residual signal is actually affected by fault, of course, but it shouldn't be affected by disturbance. The same conditions that we talked about. So what I'm going to do, don't panic when you see the next page. What I'm going to do, I'm going to substitute Y from this equation here. And when you do that, because Y is having something from U, so Y is H YU multiply U. Also, you have V multiply U. Then you have 2 terms that are having U, so you can factor from U. Now we come to this one. So if you look at that, I have just, what I have done is just substituting y to the main equation, to the bottom equation. Go back again, y from here to here. So this is what I said. So we get r, the residual. So because u, as I said, because you have two terms as a function of u, so one of them was v ru, the other one was v ry multiplied hyu. Okay. Also at the same time, I have collected u and disturbance here, but I have not touched the fault term. And also there is a term from the initial state, but I will talk about that later. Okay, so the residual, if, as I said, if we assume that residual, if v or u, we don't know yet what is v or u, we don't know yet what is v or y, but we are assuming that we multiply u by in general, u is a vector because we have multiple inputs, so therefore v or u is a matrix. Also, y is a vector. If the system is MIMO, then v or y is a matrix. But if the system is SISO, then they don't need to be matrix. They could be also scalar. So back to this equation. So I'm rewriting R, or I'm collecting the terms that are having U and D here. What I'm doing that because again, we need to get rid of that. R is supposed to be only a function of fault. So this term should be actually eliminated somehow. We'll see how. But what about this term? There is a difference actually between this term and, for example, the term that you have U or this term. The reason is that it's only a function of initial state, initial or initial value of the state, x0. So initial value of the state, it has some effect on the output. Also, it has some effect on the residual. But the point is that if the system is stable, okay, if this v or y multiply h by x is stable, then the effect of x on y will actually eliminate it after a transient response. So it's having some effect, but it would be only a transient effect. Okay, I think that's clear because you know that you have seen that before. The response, let's say for a linear system, the response would be actually the summation of two terms. One is due to the input, one was due to the initial value. And the effect of initial value on output, if the system is stable, it will actually vanishes after the transient response. It's only a transient effect. So if we have that stability condition that we call it Horwitz, by the way. Horwitz, when we say a matrix is Horwitz, it means that all eigenvalues are in the left side. So if we have this stability condition, then also we don't need to be worried about this term. It has some effect, but it will actually vanishes after some time. So if you're actually planning long term that to form the residuals for a long term, then as I mentioned, after the transient responses, this term will be eliminated. So what we are left with is only this matrix multiply this vector plus the fault. So now this matrix, the first part of this matrix, I can actually write it as the multiplication of these two. So if you notice here, V R Y, V R U multiply this matrix, it would be exactly what we had here. So it's just a rewriting, but in terms of multiplication of matrices. Again, residual is this matrix multiply that and multiply this and plus two other terms. As I mentioned, this one we don't concern. This one is okay, it should be there. We need to again get rid of this term because residual is not supposed to be a function of disturbance and input. So basically, when you change input, it shouldn't actually change the residual. So how to get rid of this term? So we can select VRY and we can select VRU. This is actually the degrees of freedom we have. So what we do, again, for this matrix, we select VRY and VRU in the left null space of that matrix. If you do that, it means that the multiplication of this matrix by this matrix would be 0. Therefore, we don't have these terms in the residual. Is that clear? Any question? So again, we are using more or less the same concept, the same trick that we had. So this using the null space, left null space. So we're selecting these degrees of freedom that we have. Actually, we selected from the left null space of this matrix, which guarantees that this term will be eliminated. But this time, you should notice that this time, the matrices we have, they are not constant matrices. They are a matrix, a function of S, Laplace S. So it's actually a bit more challenging compared to what we had, because S, when we have S, it has also some meaning in the frequency domain. So it's better when we are selecting VRY and VRU, also think about because VRY also appears here. Think about in terms of frequency response of VRY, how should we select that? Because as I said, in the null space, you don't have only one element. So how to select that in order to, for example, filter some frequencies of the fault or filter some frequencies here? I mean, we can also use this property of designing a filter while we are selecting within the null space. Still, we can be in the null space, but also it could have some frequency domain properties. That's actually a block diagram. It's nothing new. Y was the combination of 4 transfer functions, multiply these 4 signals we had, and then we are trying to generate the residual. So back to the equations we had, I said that this matrix should be selected in the left null space of that matrix. Okay. Now here it comes actually the part that is a bit more complicated maybe, because I don't know if you know, for example, how to factorize a matrix. So it doesn't matter because I try actually to do it in a simple way. So imagine that this is a matrix. This VRU and VRY is a matrix. Okay. So when I say matrix, it could be a vector, a row vector, but matrix is actually a more general term also for a vector. So a row vector is also a matrix of 1 by 2. Okay, it's just the dimension is 1 by 2. So this matrix, we write it as the multiplication of Q by F divided by P. F, now we select F in the null space of these, but Q and P, we keep it as design parameters to design the filters, as I said. F is the part that makes sure that this matrix is in the null space of that matrix, but still we can change Q and P to have a desired frequency response. Okay, so here is some condition just to check whether or not the system is detectable, but I prefer actually to go forward. I show you the algorithm, and when it comes to the example, I will try actually to clarify what I meant when I said that we use those degrees of freedom. So if I want to summarize the algorithm, you need to compute the transfer function, this transfer function, and let's name it H. And what was H? H was basically this matrix that we need to calculate the left null space for, and then try to try to find the left null space for that matrix and select f of s to be actually in that null space. What is f? If you remember, I wrote this matrix as the multiplication of two matrices divided by a polynomial. P of s is not a matrix, it's just a polynomial. It's a scalar. But Q of s is a matrix in general. It could be also polynomial, but it could be matrix. F is a matrix for sure. And F is the part that is in the left null space. And then later we need to design Q over P to have appropriate low pass or band pass or high pass filter. Okay. And finally, we need to check whether or not it is weak detectable or strong detectable. I believe the example will clarify what we meant. It's the same example that we had, and we considered that using the parity method in time domain. So A, B, C, D, and so basically we have EX and FX as well. So when I say form the matrices, you need actually to calculate these transfer functions. So these are the transfer functions we have. And finally, we need to form this matrix. So basically, that's the main matrix we have here, HYU, HYD, I, and 0. So you have calculated HYU, HYD, and I is identity, and 0. So this is H of S. Okay. So I will actually wait on this slide, and we can actually think about this matrix. First of all, this matrix is 3 by 2. Okay. When the matrix is 3 by 2, and because it has 3 rows, 2 columns, therefore, for sure, it has a left null space because the rank of matrix is 2, but you are having 3 rows. So you can find something in the left side that when you multiply by the matrix, then actually it will be 0. Is that clear? When you have a 3 by 2 matrix, always you have a left null space. But how to calculate the left null space, because you are having this S and the null function in MATLAB doesn't work, at least doesn't work as easy as it's used to when we have only constant values. So what you do, when we have a matrix transfer function like this, first we calculate the common denominator for all elements of the matrix. So the common denominator. So what would be in this case, the common denominator would be S plus 2 multiply S plus 1. Okay, so you make the common denominator for all elements. So for example, here, because you need actually to multiply the denominator by S plus 1, so the numerator would be S plus 1 as well. Okay, and the next step is actually to factor from the common denominator. So what you get is this. As I said, this S plus 2 multiply S plus 1 is the common denominator. So you factor, you take it out. So this is actually the matrix we have. At least, still we have S, but at least it is not a fraction. It is just a polynomial. So it's easier actually to work with compared to when we have transfer function, when we have fractions. So you take this one out, and you need to find a null space for this matrix, because the null space for this matrix would be the same as null space for the whole H, because whatever you find to multiply by this matrix from left and it is 0, if it makes this if that matrix that you find multiply this matrix here is 0, therefore that matrix multiply H would be 0. So it doesn't matter if you have actually taken the denominator out. Okay, so we need to find the null space of this matrix. And as I said, because matrix is 3 by 2 and you want to find the left null space, the rank is of course 2, definitely you can find. So here we have found an element for this null space. And if you want to know what it means that actually if you multiply this row by the first column, it is 0. If you multiply this row by the second column, it is also 0, because it is actually in the left knowledge space. That's the definition. If you're in doubt, you can multiply. Let's multiply this one by the first column. So 10 s plus 1 multiplied 5 would be 50 multiplied s plus 1. And then you have another 50 multiplied s plus 1 here that cancels the first one because this one is having negative sign. And then you have minus s plus 2 multiplied s plus 1. And then you have 1 multiplied s plus 2 multiplied s plus 1. So you saw that actually if you multiply this row by this column, it is 0. You can also see that this row by that column would be 0. Therefore, this is one of the elements of the knowledge space. So this is actually the solution we are looking for. Okay, but as I said, we needed actually to find a knowledge space or an element in knowledge space for the whole H. But we said that let's write that element as the multiplication of two matrices divided by a polynomial. Let me go back here. We are supposed to write it in this form. In this form. Now what we found is only f. This is the element of the knowledge space we found is only f of s, the capital F of s. Still we have, yes, this is the capital F of s. Still we have Q of s and P of s to decide if we want to filter. You can leave it, you can just ignore them. You can just assume that Q of s is 1, P of s is 1. And this solution is good enough, it works. So you don't need to add anything. If we add this Q and P, if we add them, in case we want to filter some frequencies, it is a degrees of freedom. We can actually ignore and don't use it, but we have that degree of freedom in case we want to use it. Okay, so this Q and P can be, yeah, in this example, we have selected that to be minus 1 over 3 s plus 1. If you do that, then the residual would be this. But as I mentioned, you can ignore that, and if you ignore that also, you won't have it. So this 3s plus 1, maybe when we go to the simulation session, we can actually see if we didn't select that, what would happen. But anyway, let's see what we have got. This is the same example as I said. A fault has happened at 10 at time equal 10 seconds, and this is what you get in the residual. So the residual is not abrupt, but you see that it is a strong detectability because the residual doesn't go down, it will actually stay there. And we didn't need to differentiate. The equations are a bit actually more, I don't know. It's not as straightforward as it was in the time domain. Always, I believe it's the case because the frequency domain, to understand that, is a bit, yeah, it's a bit more, I don't know. We need to pay more attention to understand what is in the background in the frequency domain. But actually, I can say that it works better because we don't need to differentiate. Also, at the same time, you have these filters to select if you want to. So you have a degree of freedom that can help you. Okay. That was actually the last slide of the parity method in the frequency domain. Still, there is one method to talk about. It's called unknown input observer. But before we go to the second, to the last method, is there any question here? Feel free to ask question, or if you need some part I passed too fast, or I don't know. Any question?
Can you explain how we determine the rank of the H matrix? Because we have S, and I'm not quite sure if that's similar.
Yeah, that's a good question. But I told you, if you have a matrix 3 by 2, the maximum rank is 2. Okay, the maximum rank is 2. In an easy way you can test it. You can set S to a specific value. You can select S equals 0. And if you want to do it in MATLAB, okay, just randomly select S, check the rank of matrix, and select a different random value for S. I do believe that if you try it twice, that's enough. Okay, so if you select S equals 0 and you calculate rank is 2, and you select S equal, for example, 1 and calculate rank is 2, then that's enough. If you want to do it in MATLAB, if you don't want to do anything on paper. But on paper, or if you want intuitively to know what the rank is 2, so here, because you have 3 by 2 matrix, therefore the rank is maximum 2, but it could be also 1. But if it is 1, it means that the second column is proportional to the first column. So you see that, for example, this term, so the second column should be again multiply of the first column if the rank is supposed to be 1. If it is the case, just notice the middle element. In the first column, you have S plus 1. In the second column, also you have S plus 1. It means that if there was a gain, it should have been 1. But if you multiply 5 by 1, you don't get this value here, which means that it is actually obvious the rank is not 1. Therefore, the rank is 2 because the matrix is 3 by 2. But because you have 3 rows and 2 columns, then rank is 2, but you have 3 rows. Therefore, you have a left null space because you have more rows. Like the example I showed you at the beginning.
Yeah, thanks.
No problem. Any other question? I also don't, I already have said that many times. I don't really like just going to the equations slide by slide, but that's actually the only way we can do that, because we have many equations, and if I want to derive in a paper, we don't have enough time actually to cover the topics. Other than these 2 presentations, there are also 2 notes, like 2 PDF files that has more explanation. So I will upload those as well. So I will upload this presentation file plus those notes, and but also you will have the video. I hope we are recording. So you will have the video, the files, and also the notes would help, because they might have some extra explanation in case you have questions. And at the end, you should be able actually to do the assignment. So you don't need to memorize anything, but you should actually understand and be able to apply the algorithm to for example, to a system. Okay. So it's 10:33. So let's have another 15 minutes, and I will be back at 10:48.